So our project is on the knuckleball. This is by Jonah Johnson, Preston Leigh, myself, Ziang Wang, and Wanliang Xing. Next slide, please. All right, so the problem is that a soccer player is taking a penalty kick. He's aiming for a spot on the goal, which is 11i, 7i, 2k meters, and needs to figure out how hard he must kick the ball to get it there. He kicks the ball and notices that the ball doesn't go exactly where he aimed. So we're trying to calculate the air resistance and its effect on the ball. Next slide, please. All right, so our soccer player, Jonah, is aiming for a spot in the goal and is trying to figure out how hard he will have to kick it. He will be kicking the ball at 15 degrees using a technique called the knuckleball, which results in the ball having no spin as it travels through the air. He will be hitting the ball from rest for the penalty kick. First, we will calculate the velocity and time required without factoring for air resistance. Then calculate for air resistance to figure out where it should exactly land. Next slide. So the assumptions that we have is that there's no wind for part one and there's no spin on the ball. The altitude is 1,000 feet above sea level and the goal is 2.438 meters by 7.31 meters. And the ball is treated as a particle in part one. And the concepts that we'll be using is our knowledge of velocity, acceleration, displacement, and Cartesian vectors. And we'll be using our newly acquired knowledge of air resistance and how it will affect the soccer ball. Next slide.
All right, so for the knowns and unknowns, what we know are the dimensions of the goal, which is 11 meters by 7 meters by 2 meters, the displacement of the penalty kick, the mass of the soccer ball, the diameter of the soccer ball, the air pressure at the 1,000-foot altitude with a 70-degree temperature, and also that the ball was kicked at 15 degrees. What we don't know and what we need to figure out is the air resistance of the ball, the initial velocity, and the time that it takes to reach the goal. So for the schematic, what we drew is kind of a neat little, we tried to make it 3D, but essentially you can see the X, Y, and Z axis, the theta, which is the angle, and then he's trying to aim it for that spot on the goal. And we use the average recommended size for professional soccer goal. That's how we got that size. And in order to make this an easier problem to solve for projectile motion, what we did was we made a new axis. And since it's a kinematics problem, we don't need a free body diagram. So by combining the XY axis, we can now use two equations for the H axis and Z axis. Solve for velocity.
So we have two unknowns, time and initial velocity. And then we have our knowns of distance in the Z, X, and Y direction. We have our angle of degrees upward off the XY axis. We have the value of H from the XY distances. And we have the equation with displacement, initial velocity times time, plus 1/2 acceleration times time squared for both the x-axis and the z-axis. And we have acceleration for in the h-axis is 0, and in the z-axis is gravity, which is negative 9.81. So here we show kind of our work. We take and we find the total displacement for the h-axis, and we plug that into the displacement equation to basically solve for time and initial velocity. Because they're both unknown, we can use substitution and substitute our value of initial velocity into the second equation, which has gravity, and we can solve for time, which we solve for 0.55 seconds. And now with the value of time, we can plug it into the first equation and solve for initial velocity, which we get 24.54 meters per second. So comparing these numbers to the real world, in a game of professional soccer, the average penalty kick goes about 70 miles per hour or 31.29 meters per second, and which means that the ball can reach the net in less than 0.4 seconds. And given our problem, considering our player is not a professional athlete, this velocity and time is pretty reasonable. And for the actual situation, so that was neglecting air resistance. So now with air resistance, as we can see here, it says, in theory, as long as we kick the football with the speed of velocity initial, which is the 24.54 meters per second, at 15 degrees, the football must be able to sit on the coordinates of 11i, 7j, and 2k, which is the displacement vector. However, since we cannot ignore the influence of air resistance on the ball cannot accurately land on the established coordinates. So our question is, where will the ball actually land?
So for this question, we first found some articles for the air resistance. Then we get here. We know that the resistance equals the equation it had to write down. And we know that whether the wind is steady or not will have a great impact on the air resistance. So we only consider the steady wind speed state here. And that's it. So please next page. And we find some survey data for the soccer ball. Yeah, we compared the wind resistance coefficients of different soccer balls at different speeds at standard atmospheric pressure during the World Cup. By comparison, we have just obtained initial velocity, which is about 88 kilometers per hour. So we adopt the wind resistance coefficient of D, it equals 0.25. And next page, please. And then we want to find A, the cross-sectional area of the football. And from the condition we already know, we know that A equals 0.038 meters square. By looking up the table, the air density we selected was 1.293. So we get RHO equals 1.293. So the picture is on the right. You can see how it comes. And the next page, please. So we can find the air resistance. We know everything except velocity. And for this question, when resistance is in the opposite direction of speed, we decompose the velocities into the h-axis and the axis. We study the motion in two directions separately, and then there's wind resistance in both directions separately. The magnitude and directions of wind resistance are changing all the time. According to our existing knowledge, we cannot establish an accurate mathematical model. So we stipulate that the magnitude and the direction of the wind resistance are always equal to the initial moment. So we get the equations. We just we can use directly use the data of the first question when no wind resistance, and we know that the initial velocity equals 24.54 meters per second. We like to solve the problem into a 2D problem, so we also use the h-axis. So along the h-axis, the ball only component in the h-axis of air resistance. So we get the equation 1 is in the middle of this picture, and we can get the acceleration 1 is along the h-axis, and for the z-axis, we can know that the ball have air resistance and its own gravity, so we can get acceleration 2. Then we get the equation 2. For this equation, we can solve out two unknowns. We don't know the time t. We don't know the time t, and we don't know the z. But we got two equations, so we can solve the two unknowns. And then it's about calculation.
Okay. So now that we have the simplified equation of motion, we have the equations of motion for the z-axis and the h-axis. We already know from the first question that the distance the ball travels along the h-axis is a century distance. We know h equal the square root of x squared plus y squared equal square root of 117, right? And we know acceleration 1 is along h-axis equal r times cosine theta over m equal 5.779, and we know acceleration 2 is along z-axis equal minus r times sine theta over m plus g, and now we know that if we want to solve for two unknowns quantity, we need to have two independent equations. Now we have the equations of motion on both axes, and we have two unknowns, t and z, right? So let's plug this into the equation. We can solution t equal 0.585 second, and z equal 1.82 meters. The ball takes longer to reach the goal than in because of air resistance. Next, please. And the ball will land at the coordinate point 11I 7J and 1.82K. This is actually. Thank you.
And that's it.